Today in this video, we're going to be looking at the multiplication rule of probability. This is the basic one. We're going to have an addition to this rule in another lecture later on. So the multiplication rule goes with the word and you want to keep that in mind. The word and goes with the multiplication rule, and I'll be demonstrating that in just a couple minutes here. But to calculate the probability of a complex, so that's a non-simple event, but something that can be broken into multiple simple events. That's what we call complex, where event A, so one of our simple ones, occurs in the first trial and event B in the second. Or there's another scenario that could happen here. The outcome of A somehow affects the probability of event B if they're if they're dependent events. So there's the what if they're independent, what if they're dependent? Then the probability of A and B, the simple version of it is it's the probability of the first times the probability of the second. You're probably familiar with this in the form of what's called the fundamental counting principle. This is taught at typically a young age when you're kind of being introduced to probability. It is technically the multiplication rule, but it's for very simple things where they're independent. And so what's going on in this case is someone's looking at picking out an outfit. You've probably heard an example like this before. They've got 2 pairs of pants to choose from. They've got 3 shirts to choose from. And how many different outfits could they possibly put together? Well, you can see here just from the probability tree that there's 6 total outcomes that could possibly happen. And any one, say, take this here, that'd be one of the 6. In short, the multiplication would go like this. You'd have 1/2 times 1/3, which of course gives you 1/6. So you can see it with the diagram, or you can just use the multiplication. 1/2 times 1/3, and of course gives us 1/6. There's a 1 in 6 chance, probability chance, that this particular outfit was going to be picked out. Let's kind of put this in context with the word or. We did or, that's of course the addition rule. Real simple here. Probability of heads on a coin, everybody knows, is 1 out of 2. And so if we get the probability of heads or a tails, well, you're going to have to add those together. And 1/2 plus 1/2 is a whole. So of course that's 100%. But if you switch it to, say, a complex event. So now we're going to have flip a coin and roll a die. These are still classic probability situations, but it's now complex. Let's say we're looking at heads and a 6. Let me demonstrate why we end up multiplying. The probability of heads is still, of course, 1 out of 2. The probability of rolling a 6 is 1 out of 6. Again, here's a probability tree or a probability diagram. So we toss the coin first. Of course, there's 2 things that can happen, but we want to go this direction. We want to go the direction of heads and a 6. We get to the numbers on the die. Well, there's only one of them that's going to give us the heads and the 6, but there's 12 things that could possibly happen here. We have to have our math match our reality. The reality says, well, there's 12 things that could happen, and this is just 1 out of the 12. So we know the probability is 1 out of 12. Now we need to match the calculation to give us that. The only way to make that happen, it's not to add them, is to go ahead and multiply. So we get 1/2 times the 6th is the 12th. And so like I said, when you see the word and, that is going to imply multiplication. If we go back to the word or, head or a 6, well, then it's going to be an addition, which in this case, you do have to worry about a common denominator. Let me just remind you about that. And so that we get 4/6, which reduces down to 2/3. All right, when you talk about the and situation, the multiplication rule, there was 2 versions of it. What if they were independent? What if they were dependent? And so let me dive into them a little deeper here. To be independent, the first event does not affect the probability of the second event. They're not in any way or shape related, similar to what I just had there with the flipping a coin and rolling a die. What the coin does doesn't have any bearing on what the die does. That doesn't affect them, so they're independent. Probability of heads and tails. So if you got two coins, one gets a heads, one gets a tails, or you could look at this as the same coin twice, but either way, heads and a tails, it'd have a 1 out of 4 probability. Dependent, though, they do somehow affect each other. One of them affects the other one, and that's the idea of they depend on each other. It's dependent probability. So take this here, the idea of in a randomized deck of cards, somebody dealing out to you 4 aces in a row. Well, that is a dependent situation because once you've got the first ace, we could talk about the probability of getting the first ace, but once you have it, well, there's only 3 left to possibly get. So the fact that you got the first one affects what's left in the deck, so therefore affects the probability of what could happen afterwards. By the time you get to, I got 3 aces, looking at the probability of the last one, there's only 1 left at that point. So this is dependent. Every time you get one of the more ace, it affects the probability of getting another ace. The probability of then has to be tweaked. What I mean by that is you take a look at these fractions. Probability of getting 4 aces. Well, when you start out, there's 4 of the 52 cards. But then to get the next one, there was only 3 aces left, and there's only 51 cards left. 2 aces out of 50 and 1 ace left out of 49. So if you were to, say, toss a coin and roll the die, would they be dependent or independent? I guess I kind of already answered this. That would have to be independent. Smoking a pack of cigarettes a day and developing emphysema. There's my coughing for that. That would have to be dependent. I think at least in the medical community, they would argue that that's going to be dependent. Conditional probability. Okay, another vocab thing for you here, and this one's got a symbol that goes with it. It's the probability of an event occurring given another event has already occurred. Here's the symbol for it. And the way we would read this is the probability of B given A has already occurred. Now this is a little bit confusing. I remember looking at this because I was thinking, well, if A's already occurred, we don't have to consider the probability of that, only the probability of B. But that's not true. We actually consider both probabilities. We just take into account that A has already occurred. For example, assume you're selecting 2 cards from a standard deck of cards. What's the probability of getting a queen given the queen has already occurred? Well, when you started out, there was 4 queens out of 52. That'd be this one actually. But then the probability of getting this queen, given that this one was selected, now there's got to be tweaked here. We've got a dependent situation. Since 1 queen has already been given that we know what happened, there's only of the 4, 3 queens left. And of the 52, there's only 51 cards left. So this one actually refers to that particular fraction right there. And that's how you would calculate that. Probability of getting a queen given a 2 has already been selected. This is still a conditional probability, and there still is a little bit of tweaking. It's still dependent, not in that there's fewer queens to be chosen, but there are fewer cards to be chosen. So with conditional probability, a lot of times you have to kind of tweak the numbers as you go. In both cases of these, we did it without replacement. It changes if you put the cards back. Because especially the second one, the denominator would then not change. And with the first one, neither number would change if we put it back. If you put it back, that's called with replacement. So we did these without replacement. If you're looking at a situation with replacement, then you have to put them back. In medical studies, they have found that actually doing a study with replacement sometimes has some benefits to analyzing how it a medication, it's usually a medication, actually can work. We don't really get into that in this class. I'm just telling you that in clinical studies of pharmaceuticals, sometimes they put patients back into the mix as to whether or not they could be chosen. The formal multiplication rule goes like this. The probability of A and B is the probability of A times the probability of B given A has already occurred. Okay, so you're going to want to write that down. The probability of A and B is the probability of A times the probability of B given that A has already occurred. So you've got some conditional probability involved with actually dealing with the formal multiplication rule. Let me give you an example here, kind of a word problem scenario. In 2007, more than 1,500 U.S. medical school seniors applied to do their residency programs. Okay, so a lot of people applied for the residency program. Of those, 93% were matched to a residency position. Of those, 74%, well, I shouldn't say it that way, 74% of them, but they had to be part of this group in order to be part of the next group. 74% of the seniors matched to a residency position were matched to one of their top two choices. Okay, so 93% were matched. 74% of those got their top choices. But there's a condition here. To be part of this group, well, you had to be part of this group to begin with. So that's the conditional part of this probability here. Find the probability that a randomly selected senior was matched to a residency program and, so this is the formal multiplication rule, and it was one of their top choices. Okay, so we've got to take the probability of them getting a residency. Well, of course, that was 93%. Then we've got to take into effect the conditional part, which actually was already just given to us as a number because it's implied that if you're part of the 74% that got one of your top two choices, that you're part of that. So it was already given part A has happened. So we just take the 93% times 74%, and there was a 68.8% chance that if a senior was matched to a residency position, that it was one of their top two choices. That's the formal multiplication rule. Let's take a look at conditional probabilities in the situation where you're looking at a chart. Again, a lot of times these are used in the medical fields. They use these charts for doing combinations of things, especially when they're doing studies, because they look at the different factors and then they'll just count people. From that, you can start to talk about probabilities. So if you look into a medical statistics book, you'll see these charts quite often. This is a blood group of Rh, so Rh factor we're talking about here, blood types, of 100 subjects. So there's 100 people here, 100 subjects. If 2 of the 100 subjects are randomly selected, find the probabilities that they are both O and Rh positive. So O, Rh positive. These are actually fairly simple to do in the fact that you're looking for the intersections of columns and rows. So you got your O here, you got your Rh there, so the intersection is going to be 39. Assume that the selection is made without replacement. What would the probability be? So if they did not put them back, so we had 2 of them. Oh, sorry, excuse me, with replacement. So if they selected them and then put that person back in, it's 39 out of the 100. And then because they put that subject back in, it was still 39 out of the 100. If this had been without, then the second one would have been only 38 people left out of 99 people. But since it was with replacement, we end up with 15.2%. And I kind of got ahead of myself there, but here's with the without replacement. So there's 1 fewer of the people in that group, and of course there's 1 fewer in the group total, and so that was only 15%. Okay, kind of a complicated one here, but let's go through a multiplication principle situation here. The human genome contains 23 DNA molecules, each containing from 500,000 to 2.5 million nucleotide pairs. I know I didn't pronounce that right, but I'm going to keep going. No more than 15% of the human genome contains DNA that helps build us. So, you know, the DNA is the instructions for the building of how we're put together. That it's the maps for protein, and it's called, the rest of it is 98%.5. They call it the junk. I think I'm missing a word there. I think there was supposed to be something in there. They're represented by 4 letters. I don't think that the letters themselves necessarily mean a ton, but maybe they do. I really don't know. A, T, G, and C, and are counted in sets of 3. Since each spot has 4 ways, so like this spot here, that could be 4 different things. It could be A, T, G, or C, A, T, G, or C, so on and so forth. It could randomly be, so if this was all put together randomly, then in a set of 3, there would be, well, that'd be 4 times 4 times 4, 64 ways that they could go together. If we were to look at the small side of the probability, so we set up here that there's from 500,000 to 2.5 million pairs. I'm just going to skip that word and go to pairs. Let's use the 500,000, the small one. In the 23 molecules, and remember that only 1.5% is used to build. The other 98.5%, that's just junk in the DNA. How many ways could the DNA molecule have randomly come together to build us? So randomness for how this all goes together, if it's true randomness, how many ways could that have possibly happened? Well, we take the 23 times the 500,000 times only 15%, but then times 64. And we get 11,040,000 ways required to, we'll just say, get it right. To have you put together the way that you're put together, to get it right. If we consider the complement to that other 98.5% of stuff not included to get it right, then we have a much, much bigger number, 724,960,000 ways to get it right. But that's if you include the junk stuff that doesn't really seem to do a whole lot. So let's go back to just the smaller number, the 11 million. So then if we looked at the probability of U happening, this is all completely random. What's the probability of U happening and turning out just the way you are? Well, to get it right then, it would be 1 out of 11,040,000, which is this very, very, very small number there. Way past a rare event. Way, way, way past a rare event. Tiny, tiny. And if you recall, we have something called the rare event rule. You can refer back to that if you want to. In the simulation of not getting it right, okay, so what if it was about, what's then the probability of not getting it right? Well, it's 100% minus that. They're complementary events. The probability of not getting it right, if it was completely random, would be 99.999, a whole bunch of 9% chance of not getting it right if it was put together completely at random. So combinations of a lot of our vocabulary here, along with obviously we've got the multiplication rule going on, 23 chromosomes and 500,000 molecules, and so on and so forth. A lot of multiplication rule. Please, in your books, find the article in this section. The title is Independent Jet Engines. This will show up on the quiz. And be able to explain how independent events turned into dependent events. Some ones to practice are on page 173, right there. Have a good day.